Okay, so I'm really happy that I had this talk, and I'm going to provide other view, computational neuroscientific view on the implementation of the emotions. And first question that, no, I don't have it. First question, what we call emotions. And for that, well, from my engineering perspective, I was looking at the computational processes that are going on in the brain. So I was interested, not just me, my group was, yeah, good. Thank you very much. Okay. Okay. So I'm going to switch to this a bit outdated. Okay, doesn't matter. So, so the question is, what are emotions, or what are computational processes that are going on in the brain, and how can we actually map that to the computational processes in the computer or in the robot, if you like. At that perspective, it doesn't matter. In 2012, this model that is called Cube of Emotions by Hugo Lofheim was published, and that bridges those two perspectives, emotions that are really high-level psychological phenomena and low-level computational, in quotes, computational neuronal processes, to be precise, that we have in our brains. And you can see the axis, that is three-dimensional model. Can I show? All right, I can. So those are three axes: noradrenaline, dopamine, serotonin, which is well-known neuromodulators that act intensively in our brain. And according to the definition of emotion by Hugo Lofheim, and actually he's based on the works, sorry, it slipped away from my head, it will come back. So based on the definition of Hugo Lofheim, emotions are short-living psycho-emotional states that we experience, we mammals, I will put it as mammals, experience during our lifetime. And many, many times we are switching from one emotional state to another. That's why you can see some untraditional, I would put it like that. So what actually model means that in zero, it's actually not zero, it's a baseline of these three neuromodulators that stands for monoamine family of neuromodulators. And then there is a high level and low level of each and every one of them. So the high level of the dopamine actually reference fear, serotonin, disgust, high level of noradrenaline, serotonin, surprise, interest, 3, all of them high, and so on. He is mainly based, he is actually a psychiatrist from Sweden, and we had published paper with him, actually as a co-author, and he is mainly referencing extreme states rather than normal states from his psychiatrist practice. What can we do with this model? So as he referenced those three, well, actually, this is part of limbic system, right? So those three subsystems, noradrenaline, dopamine, and serotonin, are actually main parts of this limbic system. And we can see those three, like dopamine is green. I'm not sure that you can see the colors, but it's like right here. And serotonin is here. It's purple, and the orange stands here for noradrenaline. So they are connected one to each other, and you see a lot of connections. Inhibitory, excitatory connections. Excitatory means increasing neuronal activity, inhibitory decreasing neuronal activity, and they have a connections with thalamocortical lobes, with the frontal, prefrontal cortex, motor cortex, and so on. We have modeled that neuron by neuron. We created a computational model of that. We have used only 3 cortical columns that will stand for those. Oh, you cannot see that, but you can see the rectangles. Number 4 is prefrontal cortex. Frontal cortex. 2 and 3 stands for motor and sensory cortex, and number 1 stands for limbic system. So we have created this model, and we managed to do the calculation of this model. We got the results. So this is actually the neuronal activity that we get from the simulation, which correspond to the medical literature, to be honest. And you see the rise and fall of neuronal activity of those cortical columns that I have just presented just yet. So the simulation was 21 seconds, and we spent like 8 hours doing this simulation. But we wanted, why was that bad? We wanted to be really close to the neuroscience. We wanted to be really close to the brain to actually fairly use this term emotions, at least from the neuroscientific, from neurobiological terms. Otherwise, what are we referencing? What is actually corresponding to emotions in biology? So yes, first of all, shame, humiliation. So low levels of 3 of them. So we see the baseline of neuronal activity with that is not really interesting, possibly. Noradrenaline, we have 2 levels. Noradrenaline, we can see the high level increases this neuronal activity, but not to the real maximum. Then it goes to the disgust, surprise. It's serotonin, mainly. So serotonin is mainly inhibitory agent. That's why we see the level of neuronal activity even lower than the baseline. Again, that corresponds to medical literature. And then we see the rise of activity when we combine serotonin with noradrenaline. And then fear is mainly dopamine, which is, well, quite high neuronal activity, and not that high when we mix that dopamine with the serotonin, again, because of the inhibitory influence of the serotonin over the neural activity of the cortical columns. And we see really high activity when we see the impact of noradrenaline over other 2 guys, which is dopamine mainly and serotonin, 3 of them, other mixture. So the interest is more like highly energetic in quotes. I mean, it means corresponds to really high neuronal activity of the cortex. And, well, that corresponds to the psychological state of the interest and of psycho-emotional state. And the anger is really high neuronal activity either. So it's a mixture of dopamine and noradrenaline. So what this is the result of our calculation that we mapped to this original model of Hugo Loeffler. It was published. The interesting point that we got, we tried to correspond the neuronal activity with the CPU resources that we used for the calculation. Yes, it depends on the architecture and so on, but we see that it's different. That's interesting. So, for example, the neuronal activity highest was in surprise, and the computational resources that we have used, or highest value was like in this intermediate state. So it's really complex profile. It's not just 3-dimensional like cube. It's not just cube. It's really complex profile that we have. And this is only 21 intermediate states only, and we have to, carry on with this research and add more intermediate states. And those are only 3 basic. We reproduced only 8 basic inborn psycho-emotional states according to the model that we have when we are just born. We have all of them where we're just born. So it's not like social, and social which emotions which will involve something like, well, at least acetylcholine. Then we have to take into account endorphins, and we have to take into account oxytocin and so on and so forth. So it kind of explodes the complexity. So we were not referencing those. If we think of the empathy, for example, right? So it's definitely based on the oxytocin, and so there is nothing like that. But this is possible. That's what I mean. And we have to understand the mechanism that underlies on the empathy, for example, to re-implement that in robots. And yes, we have tried to implement part of that system, only dopamine and serotonin, in a robotic system that was operating really small portion, I would put it like that, really small portion. If previously we'll be addressing the rat brain that we have recreated, well, the part of the rat brain that we have recreated, that I have demonstrated previously, but here we just used, I don't know, tens of the neurons here, so it's really small, but we had to fit into the constraints of real time. So that was real time. And, well, robotic systems, they don't have clusters, usually. So, but we could indicate that we could actually reproduce joy, we could reproduce disgust, and we could reproduce fear. Right. Yes. So I'm going to wrap up. So, and this robot could interact with humans in the social environment, well, at least with those basic three emotions, and demonstrate the different behaviors that actually wasn't really learned. They were really hard-coded, to be honest. But we can, that seems to be not really complex, at least. The point, modulate with those two agents the learning speed, and that wasn't implemented in that particular robot, but it's kind of understanding, we have an understanding how to do that with the serotonin and the dopamine, for example. And then we can extend that to noradrenaline further. So this is kind of first steps that we are trying to move towards. But what I can say, I just came from the conference from Memphis that was in Turin in Italy. So those two companies already have spiking, which are different to traditional spiking neural chips. And those guys from CEA, they actually provided me with some information that they can produce, for example, 500,000 of synapses on their chip. That brings us to what we call, and that we'll have a talk on Friday, Neuropunk revolution. That means that we're trying to reuse the approaches of neuroscience in electronics to help people. Here we are talking just about emotions, but I will have a talk about re-implementation of the spinal cord with those devices that are getting closer and closer to the biological scales that could be used to help humans, to help robots to communicate, inspired and being close with understanding, neurobiological understanding of the complex processes like emotions and some other, I hope. That is, I think, the way we can implement empathetic artificial intelligence and really conscious artificial intelligence that could be like really close to us, I think, I hope. Thank you.
Well, thank you, Max, for the presentation. Yeah, can I? Yeah. Okay.
Maybe you said at the beginning, maybe I missed it. Is your study gender sensitive?
Sorry?
Is your study, the one that you've shown, gender sensitive? You said those guys?
Guys, I'm here. Sorry. noradrenaline, dopamine, and serotonin. It's not gender sensitive. It's just really basic emotional mechanism. It's let's put it like that. So the brain that we've been simulating, it just appeared and was existing for 21 seconds. So there is no influence, just like born, not really born, but just appeared in the space, some virtual space, let's put it like that. And it lived 21 seconds only, that's it. So there is no actually any influence of gender, if you put it like hormonal or anything else, except that 3 neuromodulators, that's it. So it's not gender sensitive at all. This is the limitation of our computational process that we have, but I hope with these neurochips we can go further and get some, well, actual influence of hormones, of learning, imprinting, blah, 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 and all this kind of stuff. Thank you.
We'll take another quick question from Kevin.
Sure.
Just a question of clarification. So I'm not clear what takes the place of the neurochemicals in the robot model. Is the chip a biomimetic mathematical model of those neurochemicals like dopamine and so forth?
Yeah.
So it's a mathematical approximation?
Yes, yes, sure, absolutely, yes.
Okay, thank you. So if I may.
Yes, thank you. We had 2 interesting lectures related to emotions. So we opened this exciting chapter for the future. Kevin and Max presented this, one from philosophical and the other from, I would say, computer science or neuroscience. So I'm very proud that we are witnessing a very important point here at Emerge with these concepts being introduced for the future. I think they should be debated, of course. We should, and we will talk about this, whether this is good or not. But what we are indicating here, this could be very possible, the future, implanting emotions into robots and into AI systems. Important question for now, and I think we are among the first to trigger this issue. So Emerge is a very special place. I just wanted to say that. Okay.
Thank you.